Strategies to address problem soils in Saskatchewan. Dr. Jeff Schoenau, PEG, is a professor of soil fertility and professional agrologist who works in the Department of Soil Science at the University of Saskatchewan. He holds his he holds the Saskatchewan Ministry of Agricultural Soil Nutrient Management Chair in the College of Agriculture and Bioresource. He was born in Saskatchewan, completed his undergraduate and graduate degrees in the 1980s in the College of Agriculture at the University of Saskatchewan and has worked there since. His research, teaching, and extension activities deal with soil fertility, fertilizers, nutrient cycling, and soil management practices in the prairie cropping systems. He also farms with his spouse, Lynn, near Central Butte, Saskatchewan.
Great.
Take it away, Dr. Jeff.
Great. Thank you. Thank you very much, Nathan. I believe everybody can hear me and see my screen, my presentation. Yep, seeing lots of thumbs up. Super. Yeah, thanks a lot for the opportunity to come out to the SIA annual meeting and talk a little bit about strategies to address problem soils. And it's great to follow up Paul Galpern's presentation and thinking about messy places in farm fields, and it's those messy places that we often find our problem soils. And so I want to talk a little bit about and using some research examples of how we may address some of these soils through management practices. And I guess starting out first, thinking about what's a problem soil and some examples there I show soils that are affected by salts, salinity, soils that have structural problems like sodic soils, soils that are low organic matter, have poor structure, poor fertility, poor water holding capacity, and really that all manifests itself in low productivity. And I guess what we might also consider to be as Paul described very aptly, unprofitable acres, unproductive and therefore unprofitable acres. So adverse chemical, physical, biological characteristics, folks, that limit growth and productivity. And so we think about those soils, and I guess we hear a lot about soil health and soil quality and what can we do, and really what we strive to do in our attempts to improve the productivity and the profitability. Certainly key to that is improvement in soil health. And so what contributes to healthy soils? And we think about soil health, and there's a number of properties or parameters that we can measure or assess the physical condition, things like compaction or density of the soil, water infiltration and storage, soil structure as it relates to aggregate stability and formation. We have chemical properties, soil pH, salinity, available nutrients, and then down there on the bottom we have biological attributes, things like potentially mineralizable nitrogen, microbial biomass, what proportion of the organic matter is represented by the microbial population, what's its composition, what's its activity that we can assess through respiration. And I guess, folks, when really kind of ties that all together, in my opinion, is organic matter. And here in the prairies, that's a key, relatively easily measured parameter that relates to soil health. And certainly soil health problems can be created. Some very good examples of that: excessive tillage that leads to water and wind erosion, as shown there. And we experienced a lot of that. And I think back to the 1970s and the 1980s when dust storms like that were not infrequent. Some water erosion where we didn't have a lot of protective residue cover. And so those kinds of issues certainly came up, and awareness of that. And those same types of soil health issues and problems can certainly be improved through management. And I think the best example of that is the adoption of by prairie farmers, a widespread of conservation management practices, in particular the movement towards reduced and no-till, which we have the majority of adoption today here on the prairies. So I guess thinking about that, how have and how can different management practices improve health, productivity, and fertility of our prairie soils? And I guess we think about problem soils and soils of low organic matter. I go all the way back to a study that I was involved in and sponsored by Ducks Unlimited. And this was in the late 1990s, looking at specific areas of the province where we had some really nice comparisons, ability to do a number of side-by-side comparisons of marginal annually cropped land. I guess what I would use another term for is heartbreak kind of land that really didn't grow much versus right beside it, we had 5 to 12 years of grass seed down that was provided in Ducks Unlimited permanent cover type dense nesting cover leased land. And so what we did is in east central Saskatchewan and northeastern Saskatchewan, we had these side by side matches that we were able to compare soil organic carbon, which is a measure of soil organic matter. Soil organic carbon times 2 equals the soil organic matter content and nutrient supply rates. And so we had these nice kind of comparisons, kind of one side of the fence, 10 years of grass seed down that was either lightly grazed or hazed, and then this hayed, and then this cultivable comparable. And so measuring soil organic carbon or soil organic matter is needs to be done carefully and take into consideration both the concentration of organic matter or carbon in the soil and also the density of that soil. So in this study, we concentrated mainly on the surface horizon, the 0 to 15 centimeter depth. And what we found in this work, maybe not surprisingly, is significantly higher organic carbon, significantly higher organic matter in that top 15 centimeters of the grass seed down compared to our cultivated comparables, as shown there in that table there. In some cases, very substantial amounts of carbon gained in that top 15 centimeters over that 8 to 12 years of grass seed down. And so really, I think this was, to me, really showed the very important role that forages and conversion to forages can play in increasing the organic matter content of the soil and indeed also increasing the mineralization potential to release nutrients as well. A little bit later work that we did, we went further south in Saskatchewan, south of Saskatoon, into the Missouri-Coteau region, and looking at differences in carbon gains from perennial forage seed down across different landscape positions. So extending from the shoulders into the mid-slopes, into the depressions. And maybe not surprisingly, we found those shoulder positions in the landscape that had the least amount of organic matter to begin with. Those were the ones that were most responsive to increased carbon storage, increased organic matter content of the soil with that grass seed down. So certainly grass seed down increased soil organic matter, and as we were able to show in subsequent measurements, also increased important soil properties like the ability of the soil to release available nitrogen through the mineralization process. So a very effective means to improve soil quality in eroded, low organic matter marginal soils. Now, that was looking at a management practice of seeding down soils to a permanent forage type cover and its effect on soil organic matter over a number of years. I'm also interested in how does a change in management influence the organic matter quantity and quality in soils that are under annual cropping systems. So a study that I was involved with looked at soil organic matter pools as influenced by 21 years of conservation agricultural management practices in Saskatchewan. And this was a part of the Prairie Soil Carbon Balance Project. Dr. Ryan Hangs worked with myself and also folks from Agriculture Canada as well involved in this project. And kind of a neat study because there's about 90 fields across Saskatchewan that were sampled way starting back in 1996 and subsequently in subsequent years. And what we were interested in, a final sampling that we did in 2018 and comparing that to what was present in those soil samples, in those fields, as revealed in the sampling in 1996 with soil samples that had been stored and archived. So really an opportunity to evaluate how things had changed in those soils over that 21-year period as far as surface soil organic matter. And what did we find? Well, really across all those soil climatic zones, we saw gains in the mass of soil organic carbon, organic matter in that top 10 centimeter depth. If we look at it on an equivalent mass basis, which is in our published paper, in particular, we saw some of the biggest gains in those soils in the brown and the dark brown soil climatic zones that didn't have a lot of organic matter to begin with. So definite benefits in organic matter content as we have these 21 years of direct seeding, use of legumes in rotation, use of fertilizer at recommended rates, all of those kinds of compendium of conservation managements that were contributing to the increase in organic matter and also increase in a particular component of the organic matter, and that is the microbial biomass carbon, as shown there. And that microbial biomass carbon is really important in the recycling of nutrients and organic matter, and really what keeps that soil active, so to speak. So we can see that benefit there. We also measured some other things like microbial respiration, similarly seeing increased microbial respiration in those soils after 21 years of conservation management compared to what we had started out with. We also look at some other properties there, and we had the opportunity then to take a look at pH, soil pH, and interestingly, comparing the pH values from 1996 to 2018 in all of those soil samples, actually we didn't see much difference at all, as shown in that diagram. And I know we do have some concerns about declining pH, acidity in some soils in certain areas of the prairies and in Saskatchewan. But I think what this suite of samples really shows us is that a well-managed soil, conservation management, improving the organic matter, actually we really don't see much impact of another 21 years of cropping on a decrease in pH. And I think that's kind of a good news story. So really that conservation management, I think that this study really showed the benefit of increasing soil organic matter, and especially in those low organic matter soils, what we might consider to be problematic because of all of the important things that organic matter provides to the soil, like increased fertility, improved structure, and also water dynamics as well. And I guess the other thing that was I think noteworthy was this increase in microbial biomass content and activity, and that really translates into enhanced soil nutrient turnover, nutrient cycling that is very important in the functioning of the soil as a base for good crop growth and productivity. And so I think conservation management really effectively addresses soil health issues over time, and that increase in organic matter very beneficial in the overall quality of that and health of that soil. But I guess you know what we're talking about here, these kinds of conservation management practices like no-till and use of diverse rotation, use of fertilizer at recommended rates, using the 4R. I mean, that's already implemented and widespread. So I guess thinking a little bit about, what are some other things that we might be able to do to deal with these unprofitable, unproductive acres like Paul spoke about earlier. And one of those that we took a look at recently was the impact of growing salt-tolerant forages on salt-affected soils. So salt-affected soils, we're talking about soils that are affected by a high content of soluble salts, which is indicated by a high electrical conductivity. In some cases, those soils are also sodic because the salts that cause the salinity contain sodium. They're sodium salts that also cause some structural issues. And you can certainly identify these often visually by an efflorescence or a crust of salt on the surface, and also typically as well in many prairie soils we find accumulation of salts in the subsoil as well. And that salt really can limit productivity because those salts hold back the water. They have an osmotic effect. They hold back water from the plant. And so we did a field study, and this was a field study that was carried out by began by a couple of graduate students, Paul Hrisick and Gravel Wong as MSc projects, started in the spring of 2007. And we made some application of amendments. We had treatments of manure, we had treatments of humic acid, we had treatments of leonardite, which is a kind of an overburden on coal, organic material, and then seeded into these sites uh, a salt tolerant green wheatgrass called AC Saltlander. And we did this on saline and non-saline field sites in southern Saskatchewan. And in the pictures there, that's Paul Hrisick, the MSc student, and also Dr. Harold Stefoon. And Dr. Harold Stefoon was the developer of the AC Saltlander at Swift Current AAFC. He's retired now, but he was a very important a resource person in this work as well. So I guess this is kind of one of those unprofitable areas of the field that Paul talked about. And so what we had is we had a seed down of the salt tolerant grass along with the amendments, and then we had also an equivalent non-saline, I guess you might say productive area of the field for comparison purposes. And in that first year, and not untypical, that forage can be kind of slow to establish, and certainly as we measured the yield of that salt tolerant green wheatgrass after the first year, comparing here the growth in the non-saline plots that we had, plots in the non-saline portion of the field compared to the saline portions there. Our growth was in that first year was greatly restricted in the saline area compared to the non-saline, and also didn't really see a whole lot of an impact of any of those other kinds of amendments there on the growth in either the non-saline or the saline portion of the field in our RCBD plots. Now, moving along then into the following spring, which represents 1 year after seeding, pretty good growth on the plots that we had in the non-saline site in that field. In the saline site, not too bad. There's certainly some starting to get a little bit better growth in there. Some kochia weed in there, which we were able to control with a fluoxapyr application. So starting to look a little bit better. And indeed, in the spring of 2018, when we made our forage yield measurements, that grass yield in that saline area, as shown by the orange bars there, it's starting to catch up with the growth in the non-saline area. And the other thing is in that year of 2018, we were maybe seeing a trend towards those amendments having a positive effect on the growth, the biomass yield of the forage. Interestingly, particularly in the non-saline portion of the study site. Now, 2019 was a pretty dry spring, but in 2019, 2 years afterwards, when we look at the growth there, what we got for the biomass yield in the fall, as you can see there, folks, very similar yields. So actually now the growth of that salt-tolerant forage grass is actually caught up to the yield in the non-saline area. Not a lot of effect of the amendment showing up this particular measurement time. 2020, again, similar to 2019, we've got similar yields of that salt-tolerant grass in the plots in the saline area compared to the non-saline area. And so this kinds of catching up that we see over 3 years, you got to have patience. But eventually what we're seeing in this study is that the green wheatgrass is catching up in the yield on the saline site compared to the non-saline. So basically what we're getting is a palatable forage to grow well on that salt-affected land. So what's going on there? Well, when we got out and measured the roots, what was going on below the surface, that salt-tolerant grass, once it established its roots, actually was quite effective in being able to use the shallow groundwater that was present in that saline area, and also the residual nutrients that had accumulated there from years ago, going across that area, putting on fertilizer, seeding a crop, and not really having anything there growing to actually use that nutrient, fertilizer nutrient that was being applied. So it's able to tap into a resource of water and nutrients that salt tolerant grass growing in that saline soil. So moving ahead a couple of years, and I think this photo actually shows it pretty well, actually starting to see the growth of that grass looking better in the plots on our saline site compared to the non-saline area. And indeed, in fact, in 2022, when we took another set of forage yield measurements, the yield of the forage biomass on the saline site actually significantly exceeded what we had on our non-saline site. Now, the other thing that we wanted to do was to take a look at some changes that were occurring in soil properties in those as a consequence of the seed down of that grass over time. And so the years that we picked to compare were 2023 to 2017. Those were years that had fairly similar snowfall the previous year, winter, and growing season precipitation. We do have to approach this, though, these kinds of comparisons with some caution, folks, because overall, the kinds of salt's pretty dynamic in the landscape and in the soil profile. It moves up and down with water. So depending on you're comparing in dry years versus wet years, you can see some differences just because of differences in the climatic conditions. But these 2 years were pretty similar in terms of the conditions that existed the previous winter for runoff, infiltration, and then the growing season precipitation. And what we do see is we see in the non-saline, wasn't saline to begin with, so it's non-saline, but we did see a small decrease in the electrical conductivity. That's the salinity. Not really any significant effect of the amendments there. In the saline, in that top 15 centimeters, we did see an appreciable decrease in the electrical conductivity, a decrease in the salinity as a result of that 5 years of having that grass growing there. Really no significant effect of the amendments. At this time, we'd shifted from the humic acid. We'd added some biochar in there as another amendment, but really no effect of the amendments on the salinity itself. Now, we also looked at soil organic carbon mass in that 0 to 15 centimeter depth and the change 2023 versus 2017. In our unamended plots there, we could see in both the non-saline and in particular in the saline, an increase in the soil organic carbon mass in that top 15 centimeters. And furthermore, where we had our amendments like leonardite, our humic acid plus biochar, and our solid cattle manure, we could see further increases, gains in the soil organic carbon content. The leonardite, the biochar, and the solid cattle manure, that's what the SCM stands for, they were added at 10 tons per hectare. So there was appreciable amount of organic matter, of organic carbon added in those amendments. And that also explains why we see that increase in organic carbon. But I think a lot of it also has to do where we don't have those amendments with just differences in the root biomass. And comparing the root biomass that we have with that salt-tolerant forage grass compared to spring wheat in plots that we had alongside of it, we can see there much higher root biomass there in the forage grass that's contributing to that increase in soil organic matter. Not a lot of difference between what we had in the non-saline and the saline, at least at the surface. In fact, that salt-tolerant forage able to maintain its root growth even down into some of the greater depths of the soil profile where the soil salinity was a lot higher, and certainly much more so compared to the spring wheat annual crop. So what have we learned in our saline soil study? Well, I think seeding that salt-tolerant grass into that non-productive problem area where we had a lot of bad weeds, actually turning it into a valuable forage acre for livestock, cover for wildlife, indeed for pollinators, as what Paul spoke about. It seems that growing that salt-tolerant grass goes a long way to help mitigate that soil salinity by getting into that shallow water table, and that will help reduce the salt movement and accumulation at the soil surface. Furthermore, we see that those forage roots add organic matter to the soil. We see the impact of that on increasing carbon storage and soil organic matter content, which of course is important to the soil health. And the organic amendments like manure and char, we really didn't see a direct effect of those on reducing salinity or increasing growth, but they did increase the organic carbon of the soil by virtue of the organic matter that they contain themselves. So some next steps that we have in the work that we're doing, salt tolerant alfalfa varieties, and speaking particularly to salt tolerant alfalfa varieties, some new ones developed by Dr. Bill Balitku in his forage breeding program. We've got some trials with that, and they look very, very promising. And of course, with a salt tolerant alfalfa, then you have the ability then to include that along with your salt tolerant grass and have the added benefit of addition of nitrogen into that system. And finally, we're going to take a look at the effects of this long-term forage seed down on these saline soils on subsequent annual crop growth and conditions. So those plots that we've had in place for 7 years now, we're going to convert them into annual cropping and take a look at the impact that the forage seed down has had and how long that impact persists. The other study I'd like to talk a little bit about and present some data on related to addressing problem soils is really addressing the question, can we restore productivity of specific field zones? And here the specific field zones that we're interested in are those eroded knolls that have suffered past erosion, wind, water, tillage erosion. And although we've maybe been somewhat effective in improving the productivity and building them up through our conservation management practices, still have a limited productivity and some caps on production because of limitations, especially in fertility and organic matter. So through selective addition of amendments, and oftentimes those eroded knolls, because of virtue of their high pH, low organic matter content, high carbonate content, certainly could benefit from addition of phosphorus, some micronutrients like zinc and copper, and also manure to add not only nutrients but organic matter. And so a study that we recently completed, which is we termed the rebuilding the fertility, the productivity of eroded knoll soils. Dr. Ryan Hangs and myself worked on this project, basically looking and dealing with the fact that historical erosion that's occurred on those upper slope knolls and those hummocky fields that's moved the topsoil from the upper slopes down into the depressions has created soils in those upslopes with low organic matter, poor fertility, structure, poor water holding capacity. And so the question, can we address that through amendments? And so this study then began in 2020 and continued on to 2023 to look at amendments on eroded knolls in two south central Saskatchewan fields as influenced by amendment treatments. And so the amendment treatments that we had phosphorus fertilizer, a zinc, two zinc sources, a zinc sulfate, and also zinc contained in a char that was actually produced from vacuum hydrolysis of old tires, which is kind of an interesting one. We had copper sulfate, and then we had solid cattle manure, abbreviation SCM, and those amendments applied alone and in combination. And as controls, we had treatments where no amendment was added, nothing at all. And then we also had topsoil replacement as our upper level control. And this topsoil replacement really came from work that been done previously and explored and continues to be worked on by Dr. David Lobb and Curtis Cavers at the University of Manitoba. And so we were interested in comparing our amendments to nothing. And then what happens when you take that topsoil out of that depression and bring it back up on that knoll as your kind of upper level, basically trying to restore what existed there to begin with. So that was about a 10 centimeter depth of topsoil that was put on there. Then we had our other fertilizer and manure amendments. This was a soil that was pretty low in phosphorus and zinc, moderate copper fertility. As you can see there, folks, pretty low organic matter and a high pH. And the nice thing about this was those knolls were large enough that we could set up a traditional randomized complete block design experiment with four replicates of all of our different treatments. And we had four of these types of comparisons underway. So we were also able to take a look at different crops out there as well. So we had over the course of rotation in there, we had wheat, we had peas, and we had canola. So what did we find? And I guess you could probably maybe even see, and maybe part of it just has to do to the elevated height of that. But you can see some of the topsoil replacement treatment plots out there. And in the year of application, in 2020, these are the wheat yields that we achieved, and we've got grain yield there and straw yield and total in the crosshatch bars, and it's maybe easiest to see the totals. So the graphs that I'm going to show you are basically constructed all the same. So just to take you through, we've got our unamended control, we've got our phosphorus fertilizer, zinc fertilizer, copper alone, then we've got different combinations. We've got our cattle manure, different combinations of micros with cattle manure, we got our char, and then we got our topsoil replacement. And I think as you can see there looking across, we got a little bit of a response to phosphorus. We actually had a negative response to copper alone. I think if we observed in the past, when you just apply copper alone without any phosphorus to a phosphorus deficient soil, you can get actually a negative interaction, a negative effect on yield. The cattle manure looked pretty good, as well as where we had the micronutrients in combination with the phosphorus fertilizer. Our topsoil there certainly came up on the top, the king of the hill, as far as the yield of wheat in that first year. Peas we had, well, peas are a little bit different. And of course, they can fix their own nitrogen. They're pretty good scavengers. In this case, what did we see? We actually saw a response of the peas to zinc fertilization. A little bit of a negative response to phosphorus alone, maybe phosphorus-induced zinc deficiency. But again, what we're seeing here, very similar to the wheat, to where we had our combination of micronutrients along with the phosphorus or with manure. Some of our best yield. And actually, with the peas, the topsoil amendment didn't yield much different than what we had with our fertilizer and manure amendments. And I think maybe that just relates to the ability of the pea to be a good scavenger of nutrients and also to be able to fix its own nitrogen. And that certainly showed in the crop nitrogen uptake, not a lot of differences overall in crop nitrogen uptake across our treatments. We had a blanket application of nitrogen across all of them, but some higher uptake observed where we had where the cattle manure provided some additional nitrogen, and also that topsoil that had higher organic matter to begin with and a higher nitrogen mineralization potential. Our crop phosphorus uptake very much followed the phosphorus that we were adding as fertilizer, as shown there, and also phosphorus added with manure. But we also had good phosphorus fertility in our topsoil and also a lot better rooting conditions in that topsoil replacement that probably contributed to greater crop phosphorus uptake as well. Organic carbon. Really, we didn't see much difference amongst our amendments after 1 year, not surprisingly, on organic carbon, except that topsoil that we replaced with did have more organic matter in it, and so that showed up as a higher organic carbon content. And finally, looking at water infiltration influence of those different treatments, we really didn't see any effect of the fertilizers at all on water infiltration that first year. Even the manure surprisingly didn't have much of an influence on water infiltration, but it was only 1 year of manure application. So it really didn't have a big effect on organic carbon as well. But the topsoil replacement, that upper level control, certainly a lot more infiltration. And I think in part that was probably related to the higher organic matter content, but also that it had a lower density, a greater porosity that allowed a greater water entry into the soil. Now, 2021, I'm not even going to talk about that because that was a really bad drought and we had trouble getting anything to grow at all. But in the third year after our amendments, looking at the crop responses to our amendments, again, a kind of similar pattern with wheat, a response to phosphorus alone, not much of a response to the micros, but where we had the micros and the phosphorus added together in balance, where we had it added with manure, actually we were getting very similar yields to our upper level control topsoil replacement. And folks, in canola, we saw pretty much a similar type of effects as well there. Uh, Again, individually, each of those nutrients applied alone, really no significant response, really no benefit. But where we had them added together, micros and phosphorus, where we had the manure along with it, that's where we got our highest yields. Now, the fourth year, this is 2023, 4 years after we'd made those amendments, a little bit different story. And I think what was happening was some of the effects of those amendments, individual nutrients after 4 years, crop removal over time, were starting to wear out, for lack of a better term. And yeah, kind of same pattern in response to the different treatments, but really that year the topsoil as our upper level control really tended to stand up as the leader in the yield of the crops. Even where we doubled the rate of the solid cattle manure, it was pretty good, but it couldn't achieve what we were seeing there from the topsoil replacement. So it really, I think, had the longest lasting effect. So the conclusions that we were able to make from this study, we saw some positive responses to addition of our individual amendments in that first year. The combinations really tended to be the best. And I think that indicates potential both short and longer term benefits from these amendments to restoring productivity of the eroded knolls, but they don't last forever. And the combinations that did provide that balanced availability of macros and micronutrients work best. But the topsoil replacement really had the longest lasting effect, which I think really shows the importance of keeping that topsoil in place to begin with, but that it is possible to build up the productivity and indeed the profitability, I think, although we didn't do an economic analysis, but the profitability of some of these areas by putting back into those soils what they need, organic matter, a balanced availability of available nutrients within the soil. So I guess kind of take home, it's not easy. It takes time. You need to have patience, I think, even looking back at seeding down of forages into some of these problem soils. It takes a while to get established, but you need to have patience. But we can rebuild, we can restore, and we can reclaim and certainly improve the productivity and indeed the profitability of some of these problem soils that we have out in our fields. And indeed, we maybe have these kinds of, as Paul said, messy places, but I think through appropriate management, seeding down to forages, thinking about some amendments that can improve plant growth, we can turn them into productive areas in the landscape. So with that, Nathan, I think I've wrapped up my formal part of my presentations. Thanks everybody for the opportunity to come out, and to the funding folks like NSERC, the Ministry of Agriculture here in Saskatchewan, and also the folks at Agriculture Agri-Food Canada for contributing to this research work. And I'm happy to entertain questions now. So thank you very much.
Excellent. Thank you, Dr. Schoenau. First question here. Referring to pH with with zero/no-till, have you come across acidification in the fertilizer band due to both the repeated placement of nitrogen/sulfur fertilizers in the fertilizer band, coupled with the lack of soil mixing associated with minimal no-till land management?
Yeah, and I think that, and that's a very good question. And I think that's something that a number of folks have been observing, and myself as well, that in these microsite areas where nitrogen fertilizer and sulfur fertilizer is being placed at the same depth every year without mixing, you can encounter some areas in some soils, especially poorly buffered soils, soils that are low organic matter, sandy soils. You can see this a significantly lower pH in that zone. Now, I also have there's certain areas within the province. There's some areas where that's maybe a little bit more of a concern because they were already acidic to begin with. Can think of some areas in northwestern Saskatchewan and also in the southern regions. Just because of the difference in parent material, those soils don't have as much buffering ability to begin with, not as high a calcium carbonate content. In fact, as we generally move across the prairies, from Saskatchewan into Alberta, you deal with more acidity concerns. Also southward into Montana, those folks, just because of the parent material that those soils have been formed on, have been seeing this to a lot bigger extent. And I think it's something we need to be thinking about, and in some cases might even be looking at some type of an amelioration, like a lime addition. If that pH starts to drop below 5.5. So certainly something that we do see. It's worse under some circumstances than other, and something definitely to keep an eye on. We have some research work going on right now, looking at some different calcium-containing amendments and what influence they might have on properties of the soil, including some soils that are acidic.
Excellent. Have you done a cost benefit of moving topsoil to knolls? And what is the minimum topsoil depth that would make this a positive change?
Yeah, so we just employed that as a kind of an upper level control. So we didn't have any economic analysis on that. But Dr. David Lobb and his group and Curtis Cavers, who's working on his just finished up his PhD on this, they've been doing a lot of that type of analysis. And they're at the University of Manitoba. In fact, there was an article I think in one of the popular press magazines about their work. So I don't have any information on that from this study. Certainly I think when you think about increasing land values and wanting to improve the productivity of a field, certainly building up a soil and having it last a number of years, that effect the economics start to look more favorable when we're dealing with a lot higher price that folks are paying for land these days compared to the past.
Excellent. Would it be better for the agroecosystem to leave marginal lands to grasslands restoration versus trying to grow crops with all the amendments demonstrated in these experiments? Inputs and continued application would be financially unsound.
Yeah, I think dealing first with the saline areas and I spoke about in the first study, that really those amendments that we had really didn't seem to do much at all for reducing the salinity or improving the growth of the grass. In fact, I would say if anything, some of the amendments like manure, they're better off used in the non-saline areas of the field, particularly in the upslopes, those knolls that are low in organic matter to begin with. So I guess looking at the cost effectiveness of those amendments, it depends on where you are in the landscape and the soil conditions that exist there. But those kinds of marginal areas, depressional areas affected by salinity, there's water there. There's typically often residual nutrients that have been put on as fertilizers in past years. And I think just by having just seeding down some type of a mix of forage without anything else, maybe a little bit of herbicide to get rid of those weeds at the beginning, is a very effective way to get a cost effective way to get something to grow on there that has some value.
Excellent. Do you see any positive economic benefits from applying biochar?
Okay, I could have probably given a whole nother presentation on biochar itself. We did not see it reduce the salinity in that particular study I've spoke of. In other studies, where we've seen a positive benefit from biochar has mainly been under high nutrient loss conditions. Sandy soils in the black, the gray soil climatic zone, and where we could see when combined with fertilizer, they did have an effect of reducing some nitrogen losses that translated into higher yield. But I would say, in general, biochar alone on soils that, like our prairie soils, generally have pretty good cation exchange capacity, organic matter content to begin with, we really didn't see much benefit to increased yield or productivity. Some other things, interestingly, that we did see from the biochar was we saw in one of our trials the biochar significantly reduced nitrous oxide emissions when it was combined with urea fertilizer, and that again was under wet conditions.
Excellent. What is the max EC where the salt-tolerant forage variety won't perform like it should?
That's a good question. So, I mean, those I don't think you're going to see that grass grow where the surface of the soil is white. In other words, like where there's an EC's getting up in around 3 or 4 or 5. I think you're going to have some problems with establishment. Where those and actually growth, but where we had those, and I'm just going by memory there. I think those soils would be considered where we were getting, the kinds of very positive responses that we were seeing. And also, I would also say with the salt tolerant alfalfa, those were soils that had ECs around that 1 to 1.5, and that would be on a 1 to 2 uh, soil water paste. So it would be considered, I guess you might say, moderately saline. Yeah, not severely saline according to the correlation between EC and severity of salinity. Yeah.
Excellent. You mentioned about a five category of soil from gray to brown. Could you determine the characteristics of those categories to expand on that? Which characteristics led to the five category?
So those categories, brown, dark brown, black, and gray that I had for the um, uh, long-term conservation management effects. Yeah, that's very simply the soil climatic zones from which the farm fields were located on and which we took the samples of. So brown soils typically have lowest organic matter. You're maybe looking at around 1 to 1.5%. Then the dark brown, higher organic matter, 1.5 to 2.5. Black, 3 to 5, maybe higher, 6% organic matter. And then the gray soils are soils developed under boreal forest vegetation. They tend to be a little bit lower organic matter than the black, and they would probably be coming in, and I'm just going by memory here, those range of soils, I'm thinking maybe around 3% to 4% organic matter on average. Yeah.
Excellent. When applying the solid cattle manure as a soil amendment to restore eroded knolls, did you have to use tillage to incorporate it in order to grow crops, or how much incorporation should be
Yeah,
used?
no, sure. No, that's a great question. So in that trial, what we did is we actually just did a light incorporation with a tillage tool, just a shallow incorporation. We wanted to duplicate kind of what a grower would might normally do when they apply manure, and normally they will do some type of an incorporation, a shallow tillage. And part of that really, what one of the things that we were concerned about, well, as well, right on the top of that knoll, if we just put that manure on the surface and didn't do any kind of incorporation, it might be pretty susceptible to some wind erosion or water erosion just sitting there on the surface. So we did a shallow incorporation with a tillage tool.
Excellent. What was the depth of the topsoil used on the knoll areas?
The depth that we used was approximately 10 centimeters. Yeah.
Um, how can the presence of high nitrogen and other nutrients in saline soil affect fertilizer recommendations for the entire field?
Well, yeah, that's a and not only high nitrogen in those saline areas, but the big one there is really high available sulfur, present as sulfate, because the salts that cause salinity in Saskatchewan are sulfate salts. So anytime you've got even a slightly saline soil, you've got lots and lots and lots of sulfate. And if you've got a white crust at the surface, I know when we've measured sulfate content in soils that would be considered severely saline, uh, you might have as much as 5,000, 6,000, 7,000 pounds per acre of sulfate sulfur in that particular area. So if you take a core of soil out of there and mix it with the cores that came from the rest of your field, you're going to end up with a composite sample that has a really high sulfur level that really doesn't reflect what exists in the majority of the field. So it can skew the level in the sample, Nathan. And so that's why really those saline areas are areas that you want to stay out of if you're doing traditional composite sampling. And actually, I would recommend, hey, sample them separately, look at them as a separate zone, sample them separately because you're going to deal with them separately. And if you're trying to grow an annual crop in there and you're just putting fertilizer on there year after year after year and getting nothing out of it, I mean, that's an example of an unprofitable acre, as Paul Galpin talked about earlier on.
Okay. Would you say that humic acid amendments would have the same effect on soils as biochar with regards to it helping the nutrient loss, or did you see more effect with
Well,
salinity?
I would say probably the humic acid, just because the rate of application that we used was a lot lower, I think would have much less effect on the bulk properties of the bulk soil compared to the biochar. The biochar we added at 10 tons per hectare. I think our rate of humic acid addition was 200 kilograms per hectare, so a whole lot lower. So the main impact, I think, potentially of a humic acid addition to soil, especially when it's applied, with the seed in the seed row, maybe some type of a stimulation of early root growth that might be beneficial. Whereas the biochar more can impact the properties of the bulk soil by increasing the surface area, absorptive surface area, increasing the negatively charged sites, the cation exchange capacity, which might be more evident in terms of actually affecting things like retention of nitrogen or phosphorus in the soil.
Okay, excellent. In areas where saline tolerant vegetation was introduced, did you see improvements in crop yield in near the study area? And one thing I'd like to add to that is there like a a short-term rotation, like adding a forage in where you can actually see a significant benefit if with only a 1 year application of that forage?
Yeah, I think it's going to take more than 1 year, maybe 3 years, to the point where we were actually seeing the forage growth in the saline area being equivalent to the non-saline. But I guess I'd say ask me that question in 2 years from now, because now we're going to take all of those plots and we're going to convert them back into annual cropping and follow the soil and the crop growth there compared to right beside it, the annually cropped area. Actually, in the saline, it was mostly weeds. That was business as usual. So we'll have an idea of to what extent having 7 years of salt tolerant grass in there has on the yield of a following annual crop. And we're going to go wheat and then canola in the last 2 years.
Okay. Would you say the greatest priority in research, excuse me, what would you say is the greatest priority for research in this field? What is your lab planning to investigate in upcoming trials?
I guess in relation to problem soils, and I guess I kind of just described the one is okay. We've had this, positive effect of forage seed down here on soil organic matter content. On what we see some evidence, it's reducing salinity. It's able to build up some organic matter. We're getting some roots growing there. We got some. What happens when you go now? We're going to go back into an annual crop. Is there a benefit there? How long does it persist? I think one of the other areas that we're working on, and this is advances, particularly with the folks in the Crop Development Center, are some of the salt-tolerant cultivars that they're coming up with. And I think one of the ones that I'm particularly interested in is the salt-tolerant alfalfa. Some of the new lines that Dr. Bilagitu has in his program that look very promising. And then can we have actually a more diverse crop species or more diverse group of plants growing in these saline areas. And I also have a project as well with Dr. Bart Lardner with different types of salt tolerant species and looking at how that influences not only above ground forage production quality, but also how that influences below ground. So we just got into that last year, and we'll be following that into the future. So this work on the forages and its impact on the soil as well as other amendments certainly continues on in my program, Nathan. Yeah, till I
Excellent.
retire in a couple years.
Did you look into microbe diversity and how the amendments influenced it?
No, no, we didn't look at the microbial population diversity in these trials. We looked at the microbial biomass, carbon and nitrogen contents in the soil. We also looked at water soluble organic carbon and nitrogen, but not the diversity in the populations. Dr. Helgeson does a lot of those measurements. I know in some of the forage trials that I've been working on with Bart Lardner, and Bobby's also gone out and measured the diversity, but not in that particular saline soil study. But would be interesting to look at. Absolutely.
Excellent. Is Biochar is an activated charcoal. It has a tendency to absorb the nutrients. Biochar restrict the nutrient leaching and can decrease the nutrient uptake?
Yeah, and so the biochar can decrease the nutrient leaching, like nitrate leaching, holding on to it. It can also holding on to ammonium, I think, can also partly explain why you may get then reduced nitrification and denitrification and reduced nitrous oxide evolution. One of my recent MSc students, Anel Danhauser, looked at the impact of biochar addition on phosphorus and phosphorus fertility. And depending on the source of the biochar made from manure actually can be a source of phosphorus, and other biochars made from organic feedstocks that are less phosphorus dense or contain little phosphorus at all, they can actually help, as in shown in some other work that another student of mine, MSc student, can actually help to reduce some of the phosphorus that may be moved in water across a field. So yeah, chars can be both a source and a sink, depending on their feedstock and how they're actually produced as well. Um, in the production of chars, typically the phosphorus is retained, but sometimes it gets occluded or ends up bound up in a less soluble and therefore less available form.
Excellent. Is there a possibility of using alkali grass dichylus spur? I'm not sure if I pronounced that right. In whatever way in growing forage in saline soils.
Yeah, so that's I think another species of salt tolerant grass. I'm thinking I'm not a botanist, so, but yeah, I mean the salt tolerant green wheatgrass is what we worked with, the AC Saltlander. It's been around the longest, and so that's what we worked with back when we set up our trials there in 2017. But I think there's getting to be more and more development, and I would say not only of perennial forages, but also work on salt tolerant wheat and barley annual cereals that I think is kind of exciting as well. But the stick list I haven't worked with myself. No.
Excellent. Would you expect the aerial extent of saline soils to decrease with seeding them down to forages? And if you return them to areas of annual cropping, would you expect these areas to grow in area to grow over time?
Yeah, and I guess that's kind of one of the things that we are going to take a look at here when we revert them back to annual crop. But in general, I would expect having that forage there, having something that's going to grow, that's going to use the water. We were able to document that it actually lowered the water table in the landscape. Now, other things are going on out there. I mean, we also had moving from a period of wet years to dry years, and then we had back into a wet year that actually helped flush some of that salt down. So there's these temporal variations year to year that we have to make sure that we're not confusing that effect just of wet year, dry year, and how that's affecting salts moving up and down to the effect of our actual treatment that we're interested in, which is the seed down to the forage. But generally, I think we can expect that as that forage develops, those roots grow, it grows, lots of evaporation, lots of evapotranspiration that's going to help lower the water table. That's going to lower the migration of the salt to the surface. The actual harvesting of the hay itself, we found really doesn't move, it does not remove a significant amount of salt. There's very little salt in that harvested hay compared to the huge amount of salts that are present in that soil. So, mainly how you're going to reduce that salinity is by keeping that water table in check, keeping it lower, reducing the migration of water and salts upward in the soil profile.
Excellent. Well, we're just coming up to noon here. Thank you so much for your presentation, and obviously, by the amount of questions that we've had, everyone was very well engaged and curious. We'll now take a short lunch break, and the next session will begin at 12:30.